Okay, so we started talking about using these port pens, and so now we can start to do some more interesting stuff. And then Dylan reminded me last time I hadn't given you guys a project, so I'll be posting your first project assignment today. It's pretty simple, though, on turning some of the LEDs on. It's okay. Don't give them a hard time.
I was definitely getting a hard time.
We're shooting daggers at him over there. So no, I had intended to give you our project today. So we are almost where we need to be to actually start using the digital input-output pens on the microcontroller. So if you remember, one of the things we have to do, we have all these different ports, and because all the pins are assigned to different ports and they're multifunction, so we have to set right now we want to use these port pins for either switches or LEDs as general purpose I/O. And in that case, the corresponding bits in the selection registers should be 0. So there's a bit in each selection register that corresponds to a particular pin in that port. So bit 0 in selection register 1 for port 1 corresponds to P1.0. And similarly, there's 1 in selection register 0. The 0th bit there in the selection register 0 corresponds to bit P1.0. So you have to set both these to 0. Actually, that's the default when you power up the microcontroller. They're in GPIO mode. So you don't really need to set these to 0, but it's good practice to do so. And then they have up to 3 different other functions called the primary, secondary, and tertiary. You don't hear that word used very often. But, so the third function that we looked at those in a table last time. The other thing that we have to do is not just enough to declare it to be an input-output pen. We have to declare it to actually be either an input, in which case we would hook like a switch up to it. We want to read a digital value produced from some other device, either a switch, could be another logic gate that we could tie directly to this, or an output. So that's in another register called the direction register. So 0 for input mode. And then you need to write a 1 to that bit that corresponds to the pin you want to use to set it up for output mode. Unfortunately, that's not all. It's slightly more complicated than that, but not much. So we're almost there. In input mode, where the direction register is 0, or that corresponding bit, the resistor, enable register, and it's called REN, and the output register, out. So this is when it's in input mode. Normally you use the output register when you're writing data out to that pin, but it actually has a dual purpose. When you're in input mode, you can still write certain values to the output register to configure the mode of the input pin. It sounds a little confusing, but these together can be used to enable or disable internal pull up, pull down resistors. Okay, and then so here's, I'll show you how to use these and what that means in just a second, but here's the corresponding table. So if we wanted to set a pin as input, you'd write zeros to the corresponding bits here in these two, in the selection registers. You'd write a 0 to the corresponding bit in the direction register. Again, there's a direction register for each port. It's 8 bits. And then you have to, if it's an input mode, you have to set up the resistor enable. And if you put a 0 in the resistor enable, it doesn't matter what's in the corresponding bit in the output register. It's configured as an input, and you would need some sort of, if you're going to connect it to a switch, you'd need some sort of external pull up or pull down resistor. If you're connecting it to a logic gate, you wouldn't need anything else, perhaps. If the resistor enable register is enabled, then the bit in the output register is used to determine whether it's an input with pull down or an input with an internal pull up resistor. So let's talk about that, what that means. So here's our microcontroller. And if you've got a switch that's connected to 3.3 volts, the issue is you don't want to connect that directly to your input, because when the switch is pressed, it's 3.3 volts, but when it's open, it's floating. Okay. So in that case, you could hook a resistor to ground externally, but this microcontroller has this nice feature that you can hook up a pull down register internally. And then there's a driver. And then this is the input value that's actually red. And so this is with a pull down resistor. Resistor is connected between the input and ground. And then the other case you could have, and if you recall the picture from last time, these are the way the switches, the built-in switches on the launch pad are actually wired. There's no external pull-up or pull-down resistor, so you need to enable. In this case, they're wired to ground, so you need to actually enable a pull-up resistor internally. Now, not all microcontrollers are going to have this capability. If they don't, you'd need external resistors to actually, if the switch is switching in 3.3 volts, you'd need an external pull down resistor. And if it's switching to ground, you'd need an external pull up resistor. But here that's built in, you have that capability to switch these in directly in the microcontroller. In the input mode, with the resistor enable set to 0, that means you're not using, so these are disconnected in that case, in which case you need an external pull up, pull down. Should be used. And again, the two switches on the launch pad, the little development board we have are actually wired like this. Which means to use those switches, we need to set the selection registers to GPIO mode, set the direction register to input, and we want the pull down, so we have to write a 1 to the resistor enable register and write a 1 to the output register in order to do all that. Then we can actually use the switch and read values from the in register, the input register, which talked a little bit about last time. In output mode, so where the direction register is 1, you can adjust what's called the drive strength, the output current capability of the pen. Okay. In the high drive mode, it can provide up to 6 milliamps. So as long as if you're trying to drive an LED that requires less than 6 milliamps, you can drive it directly from the microcontroller. If it requires more than 6 milliamps, and a lot of the LEDs that we have, the red LEDs, are typically require 20 milliamps. You can't drive those directly from the microcontroller. The ones that are on the launch pad, it's okay to do that. The drive strength register, which is called DS, can be used to select higher drive strength. So this is (0.1) regular or high current output. Okay. So here's a simple example, and you can build off this for one part of your project actually. But so create your new project. This is the blue LED. All this does is flash the blue LED on the microcontroller at, I think it's like half a second rate or something. So you start with just a bare project with a bare main, or actually you could just delete your main and copy this, download this into your whatever project you're creating. So here we have to know which port pin our LED is connected to. And so I had these on the, go ahead and pull them up. I had them on figures last time. These are in your book, but I have them here. So we say we're driving the blue LED. So that's bit 2 and port 2. That's what the bit associated with this particular output pin. It's bit 2 and port 2 for all these different selection registers. So the port has these selection registers, the direction register, resistor enable, all associated with that port, and each of the ports does. So, I put that in here so I don't have to keep looking back for that documentation. The blue LED is connected to P2.2, and then bit 2 And any register, don't forget that there's 0, 1, 2. So bit 2 is actually 0x, 0, and 4, right? That would be bit 2. If we wanted to access bit 0, it would be 0x, 0, 1. Bit 2 would be 0x, 0, 2. And then the next bit here would be 0x, 0, 8. So these are actually predefined in a header file for you, but it's pretty easy to, I want access to that third bit, so that corresponds to a binary value of 4. So I'm going to clear out that bit in the selection registers. If you remember how we did that, you want to and then here I'm always going to use that 0x04 value. But I want to, so if I take the complement of 0x04, it's got a 1 in one position, but the complement of that would have a 0 in that position and 1s everywhere else. So if I AND with a 1, it doesn't change the value, but ANDing with a 0 is going to clear that bit. So I want to set both those bits in the selection register to 0, for general purpose I/O. And this is going to do that for me. Is that clear? If I wanted to set them, if I wanted to set it to a 1, what would I do? I would OR it, okay, with the same value. Okay, and again, here I'm doing this in such a manner that I'm only affecting that 1 bit and I'm not changing anything else. Okay. Since you're on this simple project, I could just as easily set P2 selection 1 equal to 0 and 0 out all the bits. Okay. And set P2 selection 0 just equal to 0 and 0 out all 8 bits. And put all of the port pins associated with port 2 in GPIO mode. That would kind of be fine here. It's not good practice to get into, especially on larger projects where one function, you may have one function that's responsible for maintaining some port pin, and then another function that's driving another port pin. When you call the one function, you don't want it to change the status of another port pin. Okay. So in the textbook, he calls this friendly programming, okay, where you're always just modifying the 1 bit you're trying to affect. So again, we could actually cheat here a lot and simplify the code. So I'm trying to drive an LED. So I need my direction, I need to be in output mode. So I need to put a 1 there in the direction register. Okay. In that same bit position. So in the next one, I'm ORing with that same value. If I wanted to, put all 8 bits in output mode, if they were all set in port 2, set port 2 selection 1 and selection 0 registers to 0, and I wanted to set all of them to output mode, I could just put, set the direction register equal to 0xFF. Convenient to use hex. Hex 4 is the same as decimal 4. I could easily just write 4 there, right? It's the same number. Or instead of FF, though, I would write 255, and it would accomplish exactly the same thing. And then I want to set the direction strength to high. Not direction strength, but drive strength to high. So all of this just to set that 1 pin to output mode, GPIO mode, output high drive strength. Then it's a pretty simple matter of turning the LED on and off. I just write to the corresponding output register for that port. And what I'm trying to do here is, if I set that to a 1, that causes the microcontroller to put a high value out on that pin, which will turn the LED on. And If I set it to 0, again, I got this, I'm ORing and ANDing, just affecting that one bit again. I set it to 0, it's going to turn the LED off. Now you have to be a little careful here. If I just had this in my loop with no delay at all, you could try it, comment out the delays. Well, here, I don't actually have, I don't think I loaded this one. Well, I'm not going to. This computer's too slow. It takes too long to actually load. But if you just did this without the delays, it would probably, it's turning on and off so rapidly. I'm not quite sure what it would do. It would probably be maybe turn on at some medium level, not be very bright. You may not be able to see it at all. I'm not really sure. Okay. Because remember, this thing is turning it on and off so rapidly in that case, maybe 100,000 times or 1,000,000 times per second, that you won't see it turning on and off. It's just happening too fast. So here, there's just what's called a software delay routine. Okay. And then, so there's this little delay routine. And the way I got this was I just had a for loop initially going out to like 100,000, and then timed on my watch how long that took. Okay. And I think it took like, maybe a second or something. And then I said, well, if I chop that down to 25,000, that gives me about a 1/10 of a second delay. And then, well, I made it a little nicer so you can call it with an argument to specify the number of 1/10 of a second. So the for loop here with really no body, it's just counting from 0 to 25,000. It takes about a 1/10 of a second to execute. But if I call that 10 times, I'm going to go to second, right? So this for loop is embedded in this while that decrements the value that's passed to it. So if you pass it at 10, it's going to give you roughly a 1 second delay. Pass it at 5, it's going to give you 500 milliseconds or half a second. You could make something that provided even finer resolution if you wanted, 10 millisecond delay. This is what's called a software delay or a busy loop. It's the best thing for us to use right now because we don't know how to use the timers. As we get more advanced, you typically want to avoid software delays because they're not that accurate, okay, for one thing. And then the other thing that it's possible that actually to run a multitasking operating system on this thing, okay, where it's actually switching between different tasks, like on your personal computer. On your personal computer, it appears to be running multiple programs simultaneously. It's really switching between them really quickly. So if we're doing multitasking on a multitasking operating system, you never want to use a busy loop. Okay? You want to put your tasks to sleep for a while and then wake up after half a second. Okay? So it's not actually running code so that some other tasks could actually run code. But for what we're doing, this is going to get us started. Okay? And then, so we set it, we delay half a second, we turn it off and delay another half a second. Another common error I see is forgetting that second delay. You'll turn it on for half a second and then turn it off, and for some reason think, oh, that's going to give me another half second delay, but it really never goes off, right? Because it immediately cycles around and turns on again. So you would never see it actually turn off. I don't know how to use this thing. Seemed like I wanted to do something there. What's that doing? So maybe a different way to do this, and I put it here in code, and you could try this. Again, it's just to toggle that bit every time. We can do that with the exclusive OR. If we exclusive OR with a 1, if it's currently a 1, it's going to turn it to a 0. If it's a 0, it's going to turn it to a 1. So just toggle it and then do the delay. And then my loop is just down to 2 lines of code. So it's just a different way to do the same thing. So any questions about this? Requires some very careful programming, right? You know, if you leave off an and or an or, you know, like here you're going to be setting that whole direction register. In that case, it may not matter. You can do this, like I said, without using those ors and ands in this case and actually affect all 8 bits by just doing assignment. Remember what these do, this is shorthand notation where P2 out is equal to P2 out ORed with 0x04. So it's actually reading the value that's there, ORing it, and then writing it back to the same location. This is shorthand notation for doing that. Any questions? Okay, so let's look at this one. I think I do have loaded on the microcontroller board. It's really not that much more complicated, but the idea here was to just simply turn on the green LED when switch 1 is pressed. Okay, and then it goes off. So it's working. This is switch 1 on your right. When I press the switch, lights up the green LED. So pretty simple. So, but it's important that you know what pin is connected to switch 1. So that's bit 1 and port 1, right? That's what this notation means. Okay, there's a bit 0, there's a P1.0. And then the green LED is P2.1. So since I didn't want to keep opening up my book, I just put those right here as comments in the code. Switch 1's P1.1, the green LED is P2.1. Fortunately, bit 1, they're both connected with bit 1 in their corresponding ports, but bit 1 is 0x02, right? That would be here. I want to affect that bit. Bit 0 would be 0x01, right? So I'm just using this hexadecimal notation here to keep track of which bit I'm controlling. So what do we need to do? Well, for the switch, let's set up, no, we didn't use the switch in the previous one. We're just driving the LED. So it's a little different. I'm clearing the direction register instead of setting it. Notice and with the complement instead of ORing with the value. So here I'm setting that bit in the direction register to 0. Here I'm setting it to 1. Here I'm putting 1s in both the resistor enable and the output. I've lost that. I'm standing right next to it. So that's this mode. So that's input with the internal pull up, which is what I need because these switches both go to ground on the launch pad. Right? We'll be working with our external breadboard, but when these switches are pressed, it puts a 0 here. Okay. You could try this with just an input mode. You'll see that it takes a long time then for the switch changes to take effect. Once it's pulled down to 0, it stays at 0 for a while without the pull-up, without the pull-up resistor. So here we need a pull-up resistor because of the configuration of the switches on the launch pad. If they were going up to 3.3 volts, we would need a pull-down resistor. So that's what this is doing. We configure the green LED just like we did the blue LED. GPIO, its output, high drive strength. Now here, and there's several different ways to do this. How do I determine whether that button is pressed or not, that switch is pressed? I read the input register value. You know, to change a value on a pin that's set up in output mode, I write to the output register. I read a value, and I could simply actually just assign this to a variable if you wanted to, and read all 8 bits. P1, and that would copy all 8 bits in that input register for port 1 into this 8-bit data variable. So here I'm ANDing that with 0x02. So it's really throwing away all other bits, right? If this is 1, if that bit in this input register is 1, I AND that with this, I'll get a 1. If that bit is 0, that ANDing would be a 0. Right, is that clear? I just want to test that 1 bit here. I don't care about what's going on with all the other bits. So you could do something like, if this is equal, you know, do this, if that's equal to 1, or if it's equal to 0. I'm really just looking at that 1 bit. Okay. And so, let's see, it's bit 2. So let's say this is 1. It doesn't matter what these other bits are. That's the only bit I'm interested in. I'm ANDing with, in hexadecimal, this 2. I'm off, aren't I? It's the bit 1. I'm ANDing with 2, which in hexadecimal is this. All right. We do a bit by bit AND. You know, where these are zeros, the result is 0. If this is 1, I'll have a 1 here. If it's a 0, I'll have a 0. So I'm really just checking that 1 bit. Now in C, a 0 result is false. And a 1, anything else is true. So if that result is equal to 0, that's false. But anything else is true. So this is really just testing to see if that bit is high. Okay, that input bit is high if it's 1. I could, again, you know, equal if it's 0 to see if it's 0. If I wanted. Now, what's the state of the switch when the input is high? It's not connected, right? Because when it's pressed, well, you've got a 0 there. You have to think back about how the switch is wired. I'm using pull-up resistor. When the switch is open, that input is high. Okay, either that or you looked at my comment. So, which says, okay, right here, if that is high, the input's high, that means the switch is open. I want to turn the LED off. So this is setting, you know, just like we did before, turning the green LED off. Anything else, if it's not high, then the only other possibility is it's low. Right? So in that case, we turn the switch off. Now, I put down some other code here that you might want to play around with. I was thinking, you know, one of the things that might be nice to do is actually press the switch once and get it to turn off, get it to turn on, press it again and get it to turn off. And that somewhat works. I've talked about switch bounce a little bit. You know, the way this is set up, if the switch is bouncing, it doesn't really matter. Initially, it may be turning on and off, but it'll be doing that so rapidly you won't see it. But here, if you're relying on it, you know, it'll depend on whether you have an odd or even number of bounces, whether it'll actually turn on or off. So you can see that switch bounce is a problem here, trying to run this code. You have to play around with it to actually get it to turn on or off. But, so any questions about that? Okay, let me talk just about a few more things and then I'll. Or anything you want to change here, we could easily add in another LED. Maybe we'll come back to that. Okay. What's really going on here when we do and this is going to be some deep C, capital C, not SEAC stuff, right? Deep C stuff. Where, but I want to mention it just to assure you that there's really nothing special here that's going on. This is just kind of standard C. But what's going on when we do something like this? That is equal to P1 N. And this is, reading all of port 1, all the bits in port 1 and assign. So you'd have in here, in this case, UINT8 for the type of the data variable. Or unsigned char would be equivalent. So kind of when you're working with microcontrollers, it's preferred to use these standard types where you specify the width. Okay, but it's equivalent to unsigned char. So P1 is defined as the base address of the port 1 register group. And then that address is actually typecast to a struct that defines all of the registers in the register group. Okay, so let's see if we can try and look at things here in Code Composer Studio. So what do I mean by that? So here's the code for. So if you kind of highlight P1 here, it tells you, that may be a little tough to see. It's got this really strange DIO port odd interruptible type. That's some sort of data type. It's actually a structure. Now, little asterisk means it's a pointer. But P1 is actually, it's defined as this DIO base plus 0. And I think maybe you can see that there's the full expansion. That DIO base is actually, this value plus this offset. This is actually the address of the port 1 register group. If you go back a couple weeks, we talk about the memory layout of this particular microcontroller. RAM is in one area. All the different registers are in another area. Every register has its own address. So when we're talking about these selection registers or input or output registers, they're all mapped to particular addresses in the microcontroller memory map. So when we're actually, reading from, for example, the input register, it's actually just taking this address and dereferencing it. Okay, so this is, P1 is defined to be this address. So normally you don't do that, so you get an address by allocating memory and getting an address, or taking the address of an existing variable here. Here, the address is determined by the designers of the microcontroller. It's at a particular address. So the address is hardwired in. That's where that register group lives. Now you can see a little more about that. So where are these defines made? Well, we only have one include file here. So if you expand this includes group, and I think it's in this particular directory, you can find this msp.h header file that we include. And if you look in that, it will actually automatically include another header file that depends on the particular microcontroller you're using. So this particular macro variable is defined when we compile all the code here. But really what this thing does almost immediately is include for us, we have the MSP432P401R. That's written on the back outside of your box. So if you go into the MSP432P401R.h header, okay, so this is a fairly huge header. Okay. It's got a lot of different stuff in it, but let me see if I can just find where P1 exists in this thing. That's not the P1 I want. That's the P1 I want. Okay. So you'll notice here's where P1 is actually defined. It's this particular structure, and then it's defined to be DIO base plus some offset. If you notice for port 3, it's this base plus a different offset. Port 1 and port 2 actually have the same offset of 0. Those registers are interleaved. 2 and 3 have the same offset. Okay. We can find where DIO base is defined. Go back up to the top. It's actually later down in all these, I guess. I wrapped around, it was at the top. DIO base is some other defined. It's this peripheral base plus this 4C00. Here's the peripheral base. It's at this, 400. So it's using several defines to actually, everything's referenced relative to some underlying base address. So there's this base address of all the registers, and then the peripherals are offset from that, and then port 1 is even offset from that. The last thing I want to show you here is find this guy, because this is actually, typecasting that address to a particular data type. So I think it's actually up. How do I search up? So here's where that thing is defined. It's not that long, but notice it's defined as a struct. One of the numbers of the struct is our in register, as our direction register, the resistor enable, the direction, the drive strength, the selection registers are all in there, and some others we haven't talked about yet. Okay, but they're all defined in this struct, and so all that's buried kind of here in this header file for you. There is some other stuff in this header file. I think I mentioned, if you look around. It predefines, instead of hardwiring in my 0x02, I could just use bit 1. Okay, that's predefined for you. So instead of, I could just use bit 1 everywhere where I get the 0x02. So but I didn't do that. But you could feel free to use these because they're in your code. Okay, let me just talk a little bit more about Well, do I need to say anything more about the pull-up resistors and internal, external, or we need to talk about that? Yes, no, yes. So you have a couple of options. And I don't know that one's really preferred over the other. But here, I'm using an external pull-down resistor outside my microcontroller. The key thing is not to leave the resistor off, okay? Because, you know, when I press the switch, it's 3.3, but when I open up the switch, it's floating. And it may take a while for that value to, you know, it may stay 3.3 forever. But, and this is when I have that resistor enabled, resistor equal to 0. I'm going to use an external pull-up or pull-down resistor. If I have it set up like this, so here when I press the button, I get a high. Here when I press the button, I'm going to get a low. Now, kind of your choice. You can decide what to do in software, right? I read that value. Here when the button is pressed, I'm going to read that value and I'm going to get a high. When the switch is open, I'll get a low. Just the opposite here. When the switch is pressed here, I'll read a low. And then when it's open, I'll read a high. But this is with an external pull-up. And again, this is when it's just in input mode with no internal pull-up or pull-down. What? Our microcontroller has this nice feature. And the magic that makes this happen, you can think of it at this point as little resistors actually connecting and disconnecting these, little switches connecting and deconnecting these resistors, but it's actually transistors that are used internally, okay, to make these connections. But this is the internal pull down. Internal pull down. And then similarly, if you have a switch like we have on our launch pads, and go back and look at the schematic. When you press that button on the launch pad, it connects ground to the input of the microcontroller. So we need to make sure that thing gets pulled high when the switch is open. Now, why couldn't we leave the resistor out here? So we close the switch, it's high, we open the switch, it's low. Why couldn't we just leave that resistor out? When I close the switch, I've got a direct short from 3.3 volts to ground. All right, I'm going to blow my power supply, blow a fuse or something. It's actually, when I close the switch in that case, it may not be high. Okay. You know, you don't want a direct short to ground. Okay. So these resistors are necessary in every case to ensure that doesn't happen. And I can't leave it out here either, or, you know, here, if I leave it out, replace it with a short. He also has a picture in the textbook, and we're going to go on next to something else next time to start talking about timers. But if you want to hook up, you want to turn on a hairdryer, you want to turn on a TV using a microcontroller. Okay. You can't do that directly using these digital I/O pins. You have to use a relay between the microcontroller and the AC appliance that you're trying to drive. But the idea is simply with the relay, so in your microcontroller, in the relay, you may have a transistor driver here, typically. Usually it uses opto-coupling to close a switch. So your TV is completely, this is a completely separate circuit that's not electrically connected to my microcontroller. Where this is a 120 volt source and this is my TV or my lights or whatever. But my microcontroller is controlling, and this is called a relay. Often what you use now is what's called a solid state relay. Okay. So it takes a digital input on one side, but flips a switch for you on the other side to turn on and off your 120 volt appliance. So, all right, that's it for today.
Why would I like my going to sit down with the plant? Yeah, I got that Blackburn fish must be class. I didn't even get one. I don't know. Yeah,